All right, let's take a look at your homework from last night. Page 203, you had questions 1 through 6 and problems 1 and 2. Let's start with the questions. Number 1 says to distinguish rotary motion from circular motion. Michael, what you have?
Rotary motion is the motion of a rotation, and circular motion is motion traveling on a circular path.
Okay. Did you have maybe something else, Kendall?
Rotary motion is a spin on an object's axis, while circular motion is an orbit on that object's axis.
Okay, again, I like the use of the word spin and orbit. I also like the reference to the axis, the internal axis for rotary motion, the external axis for circular motion. Though your definition wasn't necessarily wrong, it was just... Anyway. Number 2, distinguish arc length from angular displacement. Audrey.
Arc length is the linear distance from one point to another on a circular path. Angular displacement is the change in angular position, or the radian measure of the angle through which the body turns.
There we go, good. Number 3, distinguish rim speed from angular velocity, Michael.
Rim speed is the linear speed of a point on a rim, and angular velocity is a change. Angular displacement is the change in angular velocity per unit time. I think I got confused.
Yeah, so the rim speed is for a point on the object. Obviously, it's going round and round and round. How fast is it going around? Then you've got how fast is the whole body rotating. The speed of rotation or spin rate is your angular velocity. The actual forward speed of an object on the rotating body is the rim speed. So if you're on a merry-go-round, you are literally moving, right? You have a certain speed of your movement. That would be rim speed for you, even if you're not at the actual rim. For you, your relative rim point. And then the angular velocity is how fast is the entire body rotating around. Number 4, let me go back to Michael. Define 1 radian.
1 radian is 57.3 degrees.
Well, that's not a good definition because it's only approximately 57.3 degrees. That's a good approximation, but there's a better definition that was in your textbook. Very similar, actually, to the definition I gave you guys in pre-cal. I realized after class I did not give you this definition in class yesterday, so we may want to add it to notes. But, Kendall?
I put 1 radian is equal to 2 pi.
Ooh, 2 pi radians is equal to a revolution, but a radian isn't equal to 2 pi.
1 radian is the measure of an angle.
Maybe. I mean, if the angle happens to be 1 radian. Okay, flip back, if you would, from your reading. Flip back to the very first page, the second page of the chapter, page 187. Here's your definition. You see the bold term radian there at the top of the second column. A radian is the measure of an angle that, when its vertex is set upon the center of a circle, subtends an arc equal in length to the radius of that circle. Here's what I want you to write in your notes. Okay? So I'm going to add this to your notes now, if you would. Here's the way I define the radian. A radian, 1 radian, is the central angle of a circle. The central angle of a circle for which the arc length equals the radius. A radian is the central angle of a circle for which the arc length equals the radius. The central angle of a circle for which the arc length equals the radius. That's a radian. When the arc length, the intercepted arc, is the same length as the radius, that central angle of the circle is exactly 1 radian. That's essentially what they had. I was kind of expecting to copy that over since I hadn't given you the definition, but now you've got that definition for a radian. Number 5, what is unusual about radian measure, Audrey?
Unusual thing about radian measures is that it can equal revolutions or degrees, and it has no unit.
Okay, the last part is correct. This first thing that you said, it's not equal, it can be converted into degrees or revolutions. That's true. The weird thing about it is it's unitless, and we're not used to that. We're used to memorizing units that go with what? We're used to always specifying units, and radians don't have units because it's just a ratio, technically, of length to length. What are the conversions among radians, revolutions, and degrees? Michael, there were a few different things we could put here.
If you're going from degrees to radians, you multiply by pi over 180. If you're going from radians to degrees, you multiply by 180 degrees over pi. And if you want radians and have revolutions, you multiply by 2 pi.
Good. What if you have radians and wanted revolutions?
1 over 2 pi.
I divide by 2 pi or 1 over 2 pi. What about degrees and revolutions?
You convert to radians and convert to
You could, I wouldn't. Degrees and revolutions, anyone? What's the relationship? 360 degrees, right, is your complete revolution. There we go. Let's go ahead and move on. Let's review some things before we look at the problems. You can go ahead and turn the page, though. We talked about movement around an axis, and any movement about an axis in general is referred to as, class? Too specific. Angular motion. Angular motion is any movement about an axis. Now, two types of angular motion. If the axis is a separate body from the other object, so that the first object is going around a separate object, that would be considered circular motion, right? We would say that the one object is orbiting the first, right? But if the object is spinning upon its own axis, we call that, this is the more important term to know, rotary motion. Star that term in your notes. Find in your notes, star rotary motion, because that's what this chapter is dealing with, an object spinning on its own axis. An object spinning on its own axis. By the way, the object doesn't have to spin very much, right? We saw some pretty vicious football hits over this past weekend. One of them very, very serious. But if a player gets hit, even if he just falls backward, there's a rotation on the player's own axis, right? The axis now would be right around his hip area if he just falls backward. That's rotary motion, right? I'm not trying to make light of it, but that's rotary motion. Any spinning at all is rotary motion, even if it's not a complete spin, right? The bottle falling over. Well, again, its axis would essentially be here, and it rotated about that axis. It is a quarter turn, technically, but that was still rotary motion. Anytime there's a spinning effect on the object, or like what kids like to do, at lunchtime, see if you can get it to land on the cap, which this kind of bottle, very hard to get it to land on the cap and stay that way. But anyway, rotary motion, right? Anytime there's a spinning action. Michael actually answered this question, but I'm going to ask it again anyway for sake of review. If I have degrees and I want radians, what do I have to do? Multiply by pi over 180 degrees. If we have radians and we want degrees, what do we have to do? Multiply by 180 degrees over pi, because pi is the same thing as 180 degrees. Pi radians, 180 degrees, they're equal to each other. One revolution, how many radians?
2 pi.
2 pi. So a complete turn. If the bottle completely flips over itself, right, a complete turn, that would be 2 pi radians. And again, we can say radians, we could just say 2 pi, technically it's unitless. How many degrees in a revolution?
360.
360 degrees. And of course we can see the relationship. If you divide both sides by 2, that's where the pi equals the 180. We said that the angle that is turned, in this case, a 90-degree angle, that's half of a pi. The angle of turn is called the angular displacement. We represent it with the letter theta rad. Now we're used to displacement being represented by the letter d, because we're talking about from here to here. What displacement was that? From here to here, what angle was that? What angle was it displaced? Right, so a displacement can be a literal distance. You could say the cap of the bottle. What distance was that displaced? You could actually find that distance, though it would actually be what shape? An arc, right? So arc length, technically, would be the linear distance of travel for the cap. But the entire bottle, collectively, had an angle of movement. We called it the angular displacement. What was the equation from yesterday for angular displacement, theta rad? S over r. The arc length divided by the radius. So in this case, you'd have to go for the furthest most point. What was the arc length of travel divided by the radius? And if you do that, that would give you your angular displacement, which we already know would be 90 degrees or pi over 2 since it's in radians, half of a pi. We said if we wanted to track how quickly, for instance, maybe just slow falls. Maybe just slowly goes down, or maybe it's a bam, okay, whatever, right? Into the balloon. It's slowly drifting through the air. Or maybe it's bam, right off your face. I was playing with a balloon with my son, and I like to pop it off his face because it's just fun to hit the balloon. Well, anyway, he's pushing the balloon around with his nose, and he pushes it too far away, so I sense my opportunity. I happen to be walking past, so I go wham, right as he decides I need to speed up to keep up with that balloon. And it pops right on his face. I was not expecting that. He said it didn't hurt, for the record, but very much surprised both of us. Well, don't throw it in the trash, buddy. Bye-bye balloon. It was for Andrew's birthday anyway, so it wasn't Timmy's balloon, but whatever. Andrew doesn't know the difference. He has a puppy dog. So, stuffed puppy dog, not real puppy dog. Anyway, but yeah, arc length divided by radius, there's that. The speed at which the object rotates, a certain amount of rotation divided by the time it takes to rotate, we call that displacement per unit time is always velocity. However, since it's rotational movement, right, it's angular displacement per unit time, we call it angular velocity. So it's going to be this angular displacement per unit time, but we don't use the letter v for velocity. Instead, we use a Greek letter, the lowercase omega, to represent our angular velocity. Now, angular displacement, we said, could be measured in radians, but technically it's unitless. So there, when you take the radians divided by time, your angular velocity is going to be radians per second, or just per second. What per second? Just per second. Just a weird way to think. So I'm fine with if you say radians per second. Now that said, the balloon could have already been moving at a particular speed. And then I come along and whop it and give it a new speed for just a moment before air resistance slows it back down. For that matter, I give it a speed and then air resistance slows it down. So the speed changes. Well, as the speed changes in a certain amount of time, we call any change in speed or change in velocity class acceleration. Well, if it's a change in angular velocity, then that would be angular acceleration. And remember, we said change is always final minus initial. So change in angular velocity is going to be your final angular velocity minus the initial angular velocity. And we put that per unit time, that's our angular acceleration, also represented by a Greek letter. Alpha. All right, so Audrey has this down pretty well. Questions from the rest of you? All right, good job, Audrey. Make sure we have these memorized. And remember, angular acceleration, this is already radians per second, or per second. And you're dividing that by seconds again, so we get per second squared, or radians per second squared. So we're used to meters, now it's just nothingness. We're used to meters per second, well, it's nothing per second. We're used to meters per second squared, well, it's just per second squared. Or you could put radians in any one of those positions as well. You used these for problems 1 and 2 on page 204. Kendall, read problem number 1 if you would. And actually, we didn't use this for number 1.
Convert the following angles from degrees to radians: 45 degrees, 90 degrees, 180 degrees, 60 degrees, 0.5 revolutions, and 3.70 revolutions.
Now, it says round all answers starting with 3 significant digits. Now, you two, most of these are memorized, right? We know 45 degrees in terms of pi is pi over 4, 90 degrees is pi over 2, 180 degrees is 60 degrees is pi over 3. Half a revolution would have to be a single pi. We don't know the 3.7 revolutions, right? But since they wanted it in terms of sig figs, therefore decimals, we needed to use the calculator to do these conversions here. And in each case where your degrees to radians, we said degrees to radians class, pi over 180. So you're literally just going to take the 45 degrees times pi divided by 180 degrees. Now, yes, that is the same as putting in pi divided by 4 if you wanted to go that route. But we said 45 degrees is equal to how many radians? Kendall?
0.785.
And when we round to 3 sig figs, 0.785. 90 degrees is how many radians, Audrey?
1.57.
Let's see, the next one was 180 degrees. Oh, well, we already know 180 degrees class is pi, so 180 degrees then, Michael, has to be
3.14.
3.14. We could do that without the calculator. 60 degrees. Again, you could do pi divided by 3 or 60 times pi divided by 180. And what do we get here, Kendall?
1.05.
1.05. When we round, we said 0.500 revolutions. We said it would have to be class pi, or 3.14, right? Because 2 pi is a whole revolution, is half a revolution, it's 1 pi is 3.14. And then the 3.70 revolutions. How do I go from revolutions to radians, class? Multiply by 2 pi. So we take 3.7 times 2 times pi, and what do we get for the 3.70 revolutions, Audrey? 23.2. Notice degrees, use the degree symbol. Revolutions, just use rev. The others use absolutely nothing. Or if you wanted to put rad every time, you could. I'm lazy, I don't want to. Questions on number 1? Kendall, you're the one I'm more concerned about because they've seen all this before. Did you get all those? Any questions at all? All right. Now, with these equations here, right, we said that these are our basic equations for the beginning of the chapter. But it said if we remember that displacement, meaning movement from one point to another, has become an amount of rotation, a rotation from one position to a rotated position, D class becomes replaced with theta rad. We said velocity is replaced with angular velocity. We said that acceleration is replaced with angular acceleration, alpha. If that's true, and time remains time, time does not change, it's scalar, no issues with time. Time of rotation, time of forward travel, doesn't really matter, time just presses on. Though one could argue technically time is always in a state of angular displacement because of the clock, but anyway, because it's going round and round. But we had 2 other equations that I gave you at the end of the hour yesterday that we didn't get a chance to use. What were those other equations from yesterday? Looking back at your notes. Kendall, give me one of them. They weren't really new, we just took an old equation, translated some pieces to make them angular in nature. Right at the end of the hour yesterday.
Omega sub f squared equals omega sub I squared plus 2 alpha theta rad.
There we go. And then the other one, Michael?
Theta rad equals omega sub I t plus 1/2 alpha g squared.
There we go. So these were really, I guess you'd say, 5 equations that we have. None of them new. Again, all of them are old. We just made some substitutions. So hopefully that'll help you to memorize them a little bit better. We were using primarily these equations, though, in the homework problem number 2. Go ahead and read problem number 2 for us, if you would, Kendall.
An automobile engine maintains an angular speed of 3 times 10 to the 3rd RPM for 12 seconds. How many revolutions does the engine make during this time? Find the angular displacement in radians. Find the angular velocity in radians per second.
All right. RPM. What does RPM stand for, class? Revolutions per minute. By the way, those of you who drive, have you noticed there's what's called the tachometer on the dashboard that shows you how many revolutions per minute? And it says 1, 2, 3, 4, 5, 6, 7, 8. Some vehicles may go all the way up to 9. At the very end, it's red because you don't want to go there, right? Those are thousands of RPMs, right? So this is a pretty realistic number. And 3,000 RPMs is about where you want to stay. Lower is better because you're getting better gas mileage. So the higher the number, the worse your gas mileage. Ever had to gun it to get around somebody or speed up to merge on the other side? You notice not only is the speedometer going up, but the tachometer is spiking as well. Usually up around 4,000 or 5,000 RPMs. It shouldn't go much higher than that unless you're being bad. Anyway, lower is better, right? If you can sit right around 1.5, so 1,500 RPMs, you're getting pretty good gas mileage. Around 2 is fine. Get up around 3, your gas mileage is diminishing. But that's what we've got here. An angular speed, a rotating speed, a revolution per minute of 3,000 RPMs. So 3,000 revolutions per minute. And it does this for 12 seconds. So this is the angular speed or the angular velocity in terms of revolutions per minute, and it says it only does this for 12 seconds. What fraction of a minute is 12 seconds? 12/60ths, of course, which would reduce to... Oh no, we've forgotten our 12 times tables. It's a fifth. Audrey remembered it. There we go. So this is a fifth of a minute, right? So the first question they ask is, if it does 3,000 revolutions per minute, and it does it for 12 seconds, how many revolutions is it making? Well, the easiest way to think of this is 3,000 revolutions in a whole minute, but it only does it for a fifth of a minute. So we're not going to get 3,000, we're going to get a fifth of that, which would be 600. So this is just number sense. This was just them testing to see, do you have some number sense, some number awareness, 600 revolutions, or 600 point, I guess, because it's 3 sig figs? Yeah, 600 point revolutions. That was the first answer they were going for, and that was purely, could you figure out that 12 seconds is a fifth of a minute? Okay, or 12/60ths even would work as well, technically. All right, letter B, let's come to that, because that begins to use a little bit more with the formulas and such. And it says, find the angular displacement in radians. Now, to find angular displacement, we have this equation, but theta rad equals S over R. Again, what is S representing, class? Arc length, inexplicably, right? Well, I say not totally inexplicably, but weirdly enough. Arc length divided by radius. Do I know the radius of this revolution? Do I know the arc length that is being... No. So I can't use this equation to solve for theta rad. But I do have another equation that can be used. One right here. Because if I just cross multiply, I could say that theta rad can be found multiplying omega times time. Now you might also say you could use this equation. And since it maintained a constant angular speed, no acceleration. Omega sub I, which is really just omega times time. So either way you want to think of it, you get to this point. The key is the omega can't be in revolutions per minute if we're going to do it that way, right? So I should use dimensional analysis here. We'll take the 3,000 revolutions, put it over a minute, min it, and multiply by what fraction here, Michael?
1 minute equals over 60 seconds.
A minute over 60 seconds. And also, Kendall, I want radians per second. I have revolutions per second. How do I get rid of revolutions? Revolutions to radians, what's the equivalency? 1 spin is 2 pi. So we would say that a revolution is 2 pi radians, right? How do I put that as a conversion factor?
2 pi radians is 1 revolution.
There we go. So we can multiply by 2 pi divided by 60. 3,000 times 2 times pi divided by 60. And so what is the omega in terms of radians per second going to be then? Anyone?
314.
314 radians per second. 0.159 blah, blah, blah. Okay, but roughly 130. We're going to put that in the memory of your calculator, store 1. And we'll multiply that by time. Well, the time is, class, 12 seconds. So we can multiply that by 12 now. And what is the angular displacement?
3,769.
0.91 blah, blah, blah. Rounded off to 3 sig figs.
3,770.
And you don't have to say rad or radians. You could just say 3,770. And if you don't see a unit, it's presumed to be radians when you're dealing with an angle. This is one way to approach it. There is another way, perhaps an easier way, that doesn't even require a formula, just a fact. We just said, letter A, that during the 12 seconds, it makes 600 revolutions. Remember, every revolution is 2 pi. So perhaps an easier way to get it would just be
That times 2.
600 times 2 pi, and you'll get the same answer. Either way would work for that 3,770 radians. Letter C, Find the angular velocity in radians per second. We did that. It's in the memory of our calculator still. 314 radians per second. Or again, if you want to just say per second, you could do that as well. Though they did say radians per second, so it's not a problem to say radians per second there. How do we do on number 2? Got A and B. You missed C. Do you understand how to use dimensional analysis to get C? Because again, a lot of times you're going to have revolutions per minute given to you. So dimensional analysis, divide the 60, multiply the 2 pi, converts it into radians per second. Kendall, Audrey, feedback, questions, comments?
I didn't really understand it when I did it last night, but I got it now.
Does it make sense now? All right, question? All right. Go ahead and flip back to page 189. Let's do a little bit more math before we move on. I want to make sure we've got this down pretty well. And look at example 13.3 here. Any of you have ever been in a revolving door? Anyone ever get in there and be like, no, wait, how do I get out of this thing again? I don't know. It's not that hard. Like, you walk in and you walk off. But, or like one of the roundabouts here in Columbus, and you're like, it's really not that hard, people. You make sure nobody's coming. You get in the roundabout just as soon as you can, and you go where you're going. Like, I'm just going in circles. Nobody else can go because I'm still here. Anyway, boy is caught in the revolving door, bless his heart. Going faster and faster, and then it's like, it's time to get off. Whoa. Anyway, went to a trampoline park with my 2 older kids, and I'm at the age where I might maybe not be doing trampoline parks. Like, when I can feel my brain hitting my skull, or at least that's the illusion I feel, right? It's like, yeah, I might be too old for this. Maybe I should, you're bouncing, just having a great time, finally getting over the weird feeling inside my brain. And then I go to stand there and I'm like still doing this. I was like, anyway, I think next time I will watch. They can bounce on trampolines. But anyway, the guy there is now decelerating, sort of. His head is spinning, even though the rest of him is trying to stop. Anyway, example 13.3, go ahead and read that for us, Michael.
A grindstone has a constant angular acceleration of 3 radians per second squared. If it starts from rest, find the angular velocity 2 seconds later.
All right. So again, this would be like the heavy stones used to grind, mill, or flour back in the day. Start speeding it up. It's just sitting there, right? So you got to speed it up to get it to a speed enough that it can actually grind stuff down. And so anyway, it starts from rest, and that's important to know because when something starts from rest, class, we would say it has initial velocity 0. Now in this case, it's not going anywhere; it's just spinning. So it's not an initial velocity of 0, but an initial called angular velocity, an initial angular velocity of 0. How do we represent angular velocity? Omega sub I is 0 radians per second. It's starting from rest, 0 radians per second initially. It gets up to an angular speed of, well, that's what we're finding, isn't it? So we're finding the final angular velocity. They tell us, Michael, the
constant is 3.0 radians per second squared.
That's the angular acceleration. It says so in the problem, right? So alpha is a 3.00 radians per second squared, 3 sig figs? 3.0 radians per second squared. And the other number that they gave us, Kendall, was the time was 2.0 seconds. All right. Just like we did back in chapter 6 and chapter 7, when we worked with these types of problems, list out what you know, list out what you don't know. And then ask yourself, what equation has these 4 things in it? And which one does?
W sub I squared equals...
No, that's the W sub F squared equals W sub I squared plus 2AD, not 2AT. It's a much easier equation.
The omega final minus initial over t.
The acceleration equation, right? Remember we said that A equals V sub F minus V sub I over T. Well, alpha equals omega sub F minus omega sub I over T. And after all, if the initial is 0, omega sub F over T equals A, or alpha rather, you just say alpha times T. Angular acceleration times time, you can do that in your head. 6 radians per second, or 6.0 since we're running with 2 sig figs here. Questions on that? Same type of approach. But if you have to know the equations, just like we had to know them in chapter 6 and 7. Know the formulas, pick the formula that has what you need, plug in the numbers. Look at example 13.4. Read that for us, Kendall.
A Ferris wheel starting from rest attains an angular speed of 1 revolution per minute in 2 minutes. What is the angular acceleration in radians per second squared? What is the angular displacement after 45 seconds? Assume the acceleration is v.
All right, so Ferris wheel, it goes all the way around, but it takes a whole minute to do it. And for that matter, it takes 3 minutes just to get up to that rate of speed. So it's moving kind of slowly. It says, what's the angular acceleration? So again, clearly we're finding alpha here. And it says it starts from rest. So again, class, we know that
The initial is 0.
omega sub I is 0 radians per second, or 0 per second. It's going to get up to a speed of
1 revolution per minute.
1 revolution per minute. That's going to be the final angular velocity. Can I use revolutions per minute?
2 pi.
No. Change the revolution out for
Pi.
2 pi radians and change out the minute for 60 seconds. This is poor man's dimensional analysis, and it works faster. Right? What does that come to as a decimal? 2 pi over 60.
0.1047.
Go ahead and put this in the memory of your calculator. So it's going to get up to 0.1047 blah, blah, blah radians per second, but it's starting at 0. And it says it takes how long to get up to this speed?
3 minutes.
It takes 3 minutes. Well, again, can I use 3 minutes?
No.
I'm going to have to change that and say
180 seconds.
180 seconds. Question is, what's the angular acceleration? Well, once again, what equation do I need to use, class?
Final minus initial over 2.
Alpha equals omega sub f minus omega sub I over t. Right? We're finding the omega, the alpha. Again, initial angular velocity happens to start at rest, so we can call that 0. We're going to take our memory value, divide by time. It's going to be a very small value, isn't it? You'd expect that. It's moving very slowly. At least its spin rate is. Now, if it's a big Ferris wheel, you're sitting on the rim, of course, and you're going all the way around in 1 minute. Maybe it does feel like you're moving quickly, but the Ferris wheel itself is moving very slowly as a rotating body. Very tiny number. What do we get for the acceleration here? Audrey?
0.00058 1. Yeah.
All right, very, very tiny number. That looks about right. And 2 sig figs? 3 sig figs? 2 sig figs. So 0.00058. And what do we measure angular acceleration in class?
Per second.
Acceleration used to be meters per second squared. Now it's
Radians.
radians per second squared. Or, as Michael started to say, just per second squared. They use scientific notation in the book. More power to them. 5.8 e negative 4, 4.00058 radians per second squared. Questions on the first part of the example. Starting to see how this is similar to what we did earlier in the school year. Okay? Figure out the values, plug in the numbers. Now there's a second part to this. Because then they say, okay, how much rotation has occurred in just the first 45 seconds? They don't say it that way, though, do they? They don't say how much rotation has occurred, class. They say what is the... Do you realize that is the same thing? When it says angular displacement, you've got to be thinking that's an amount of rotation. Not the rate of rotation, omega, but an amount of rotation, theta. Does that make sense? Angular displacement, we have to equate with an angle that is theta. And it says after 45 seconds. So now we're going to change the time component to be only 45 seconds. The initial angular velocity is still 0 radians per second. Class, is it up to this speed yet? It took 3 minutes to get there. We've only been going for 45 seconds. I do not know that the final angular velocity is 0.1047 blah, blah, blah radians per second yet. It's not that yet. It's something less than that. But I do know it has a constant angular acceleration. So the alpha value that's on your calculator, the 0.00581 blah, 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 put this in memory too. Hopefully that's still on your calculator. If not, go ahead and recalculate that value. So we know we have memory 2 for the alpha. And the question is, how much rotation does occur? What is the angular displacement, class? We're finding theta rad. What equation has these variables? big ugly one,
Yeah.
right? The theta rad equals, say it with me, omega sub I t plus 1/2 alpha t squared. Now, saving grace, omega sub I is 0. So the whole first term class, gone. So all I have to do is take half of my memory times time squared. Half of the memory times 45 squared. Still not a big number. Not a lot of rotation has taken place yet. But what do we get? 0.589 blah 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 radians. Or approximately 0.59 radians. Alright, questions? They have rounded to 0.60. I'm wondering, are they wrong or did we use a rounded value? Did we use the exact value from this?
I used the exact.
You straight up 0.589? Time for me to fact check them. Alright. Let's see. And divide that by 180. Okay. I got the same thing, so they are incorrect. I'm not sure why I hadn't fixed that in the book yet. 0.589, blah, 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 rounds to 0.59 radians. And again, remember, a radian, to what Michael said earlier, it's not the definition, but it's a good thing to keep in mind. That's about 57 degrees, right? 57.3 degrees. This is only about 6/10 of that, about 60% of that. So it's only about 25 degrees. It took 45 seconds for the thing to rotate, that much. Moving very, very slowly. Questions on the example problems? All right, I want you now to turn over to page 204. Page 204. Very similar problem, except they didn't give you revolutions per minute, which is nice of them. I want you to do problem number 3. They're on page 204. Problem number 3 on page 204. Did we get these answers for problem 3? Kendall saying yes. Did we at least get the alpha correct? So we got the first answer correct. Did we use the correct equation for the second half? Yes.
I didn't want to use the calculated value, so I used a different equation.
Ooh. What equation did you use?
I used the omega equals theta rad over t.
Oh, okay, here was the problem. You assumed it was at this speed already, though. But remember, it took 60 seconds to reach this speed. It wasn't at that speed yet. That was the problem, okay? So at least we know what we did. Audrey, you said you did use this equation.
That was just a mistype.
Okay, mistype. All right, well, my question was, did you maybe forget the half or forget to square? Because those are common mistakes, but just a mistype. All right, take a look at number 4. At your seats, do number 4. Actually, for sake of time, hold that thought. We're running just a little bit behind today, so I am going to modify some things here. All right. All right, next thing we need to get to, all right, because we do need to get to something before the end of day today, and that's the correlation between linear and angular, and I think this makes sense to you. The faster that a wheel is spinning, the faster an object on the wheel is moving. Understood? Right? We also understand this just from our merry-go-round days. You remember the disc, merry-go-round, just a big flat disc, and you stood on it and it spun around, and you could stand anywhere on the disc, right? Not like the merry-go-round, well, I guess technically even the merry-go-round like that they had at the mall before with the horses and stuff, the carousel, or you could sit on the inside, or you could sit on the outside. There were still 2 different places you could be. We understand this, the further out you get, the faster you will be moving. Understood, right? A little wheel spins at the same rate as a big wheel. We know this from our machines, right? The wheel and axle, right? Little wheel turns at the same rate as big wheel. The big wheel is actually moving faster at the rim. So we understand there's this correlation between the spin rate and literally how fast the object is going. For instance, a car. The faster the wheels spin, assuming you have traction, the faster the car goes, right? That's the idea. You're actually accelerating the wheel spin rate. As a result, the car moves forward faster. So there's definitely a correlation between linear, meaning forward progression, and angular. And again, when I say linear, it means curvilinear in many instances, because you're not traveling on a straight line path, but the forward advance of an actual object versus the spin rate. Linear, again, refers to any point on the rim of the body. Angular refers to the rotation of the entire body. Well, we already know from our definition of arc length, theta rad equals S over R, S equals R theta rad, right? Well, arc length is a linear, curvilinear distance, right? From one point to another. So arc length is S. Theta rad is the angular displacement. So linear displacement we call arc length. The angular displacement would be theta rad. The distance an object travels along the arc, the amount that the body has spun, and S equals R, theta rad, correct? But I want you to think now about the velocity. Well, the velocity of any object is the distance it travels per unit time, correct? So what about that's you on the merry-go-round? Round and round and round and round you go, right? But as you're going around, you're traveling a certain distance. Now, it's all along a circle, but you're still going a certain distance, correct? The distance you travel literally is your arc length. Now, your arc length may be several circumferences long, but your arc length is the linear distance, correct? And we know that S equals R theta rad. But we also know that theta rad over T is omega. So that a linear velocity is equal to the radius times the angular velocity omega. Does that make sense? So for velocity, linear velocity is the radius times the angular velocity. Well, consider this. We know that acceleration of a body, and yes, if you were standing on the merry-go-round and someone starts to turn it, as they turn it faster and faster and faster, you begin to go faster and faster, right? Your acceleration is your velocity change per unit time. Well, but if this velocity is, as we just said, r omega, then A is r omega, or the change rather, over time, correct? Well, what is change in omega per unit time? Angular acceleration. So that A can be thought of as the radius times the angular acceleration. Do you notice a pattern? The linear value, whether it's displacement, velocity, or acceleration, although we change them over with these letters, they're actually going to be equal to the radius times the angular. And rather than memorize all three of these equations, I want you to memorize this rule. Linear equals angular times radius. Linear equals angular times radius. So if you know the spinning speed of an object, you know how fast an object on the rim would be traveling. If you know how much total spin has taken place, you multiply that by the radius, you have the total arc length. You take the change in spin speed times the radius, you know the forward change in speed as well of an object at the rim. Linear simply equals angular times the radius. Memorize that one rule, you don't need these equations at all. Okay? We're going to use that in the last homework problem that you'll have this evening. Homework is to do page 204, problems 4 through 6. Page 204, problems 4 through 6. And we'll look at all of that in our next lesson. All right, have a wonderful rest of your day, and you are dismissed.